Somewhere out there, 400 billion stars are burning in our galaxy alone. Most of them have planets. Many of those planets sit in the warm zone where liquid water can pool. The math says life should be screaming across the sky, radio chatter, engineered light, fleets of probes drifting between stars. Instead, we get nothing. Pure, cold silence. Tonight, we ride that silence. We pass dead worlds, hunter theories, sleeping superminds, and a filter that may already be closing in front of us. If you want to know what the universe is actually doing, hit subscribe and stay close. Strap in. The mission begins now. Los Alamos, summer of 1950. 4 physicists walking to lunch. They are joking about a New Yorker cartoon showing aliens stealing trash cans from New York City. Edward Teller laughs, Herbert York laughs, Emil Konopinski laughs. Then Enrico Fermi, the man who built the first nuclear reactor under a football stadium, goes quiet. They sit down. They order. The conversation drifts to other things. And then, out of nowhere, in the middle of the meal, Fermi looks up from his plate and says 6 words that will haunt science for the next 75 years. But where is everybody? Nobody at the table needed him to explain. They all understood instantly. Our galaxy is old. Older than dirt, older than the rocks under your feet, by a factor of 3. The Milky Way has been spinning for over 13 billion years. Stars like ours have been forming and dying for almost all of that time. If even one civilization had appeared a few million years before us, a blink of an eye in cosmic terms, they should already be here. Standing on Mars, mining the asteroid belt, leaving footprints on every habitable rock between here and the galactic core. Yet the sky is empty. Not quiet. Empty. Fermi was not asking a poetic question. He was running a back-of-the-napkin calculation in his head, the same way he once estimated the yield of an atomic bomb by dropping torn paper from his hand during the Trinity. Test. He calculated travel times. He calculated colonization rates. He calculated how long it would take a single curious species to spread from one star to the next, even at speeds we already understood in 1950. The answer terrified him. A few million years, tops. The galaxy is 50,000 times older than that. So either we are first, we are alone, or something is wrong with the picture we have been painting of the universe. And here is the part that should make your stomach drop. In 1950, this was a thought experiment, a clever puzzle over pasta. There were no exoplanets confirmed, no water on Mars, no evidence of organic molecules drifting through interstellar clouds. Fermi was asking the question with almost no data. Today we have the data. Mountains of it. Telescopes the size of football fields, probes pushing past the edge of the solar system, ground arrays scanning 1 million stars at a time. We have looked harder, longer and deeper than any generation in human history. And the answer keeps getting worse. Because every single thing we discover, every new ocean world, every new Earth-sized planet in a habitable zone, every new amino acid found drifting in a comet, should be raising the odds that someone, somewhere, is out there making noise. Instead, the universe stays locked in this perfect, impossible quiet. The radio bands are clean. The infrared sky is clean. The optical sky is clean. Something is keeping the lights off. What started as a lunch table joke has hardened into the most serious question in modern astronomy. And the men at that table, brilliant as they were, had no idea how much darker their question would get once the data started rolling in. The first crack in the silence came from a man counting planets he could not see. In the early 1990s, an astronomer named Geoffrey Marcy was considered a fool by half his profession. He was hunting for planets around other stars. Most of his colleagues thought such planets, if they existed at all, would be impossible to find with the technology of the time. Funding committees mocked him. Telescope time was almost denied. He kept going anyway, watching for the tiny gravitational wobble a planet would tug into its parent star. Then, in 1995, a Swiss team beat him to it. They found a giant planet whipping around a star 50 light-years away. Inside a year, Marcy confirmed the result and started finding more. The floodgates cracked open. By 2009, NASA launched a telescope called Kepler, and the trickle became a tidal wave. Kepler stared at one small patch of sky for 4 straight years, 150,000 stars in its field of view. It watched for the faintest possible blink, the shadow of a planet crossing the face of its star. The dip in light was sometimes less than 1 part in 10,000. Imagine spotting a moth fluttering past a stadium floodlight from 1,000 miles away. That is the precision Kepler delivered. The results rewrote the textbooks overnight. Planets are not rare. Planets are everywhere. The data showed that almost every star you see in the night sky has at least one world orbiting it. Many have entire systems. Rocky worlds. Gas giants. Worlds tidally locked, with eternal day on one side and eternal night on the other. When the statisticians ran the final numbers, the result was staggering. Our galaxy alone contains somewhere between 40 and 100 billion planets. Of those, an estimated 11 billion are roughly Earth-sized and sit in the temperate zone where liquid water could exist on the surface. 11 billion. In one galaxy, and there are 2 trillion galaxies in the observable universe. Here is where the silence starts screaming. Before Kepler, you could comfort yourself with a simple excuse. Maybe planets are rare. Maybe Earth is a freak accident, and most stars have nothing orbiting them but dust. That excuse is dead. Buried. Cremated. Every empty star Fermi worried about in 1950 is now confirmed to have neighbours. The cosmic real estate is fully booked. So where are the tenants? The Drake equation, written by astronomer Frank Drake in 1961, was supposed to give us a way to estimate how many talking civilizations should be out there right now. It multiplies the number of stars by the fraction with planets, by the fraction with life, by the fraction with intelligence, and so on. In 1961, almost every term was a wild guess. Today, the first 3 terms are no longer guesses, they are measured. And every measurement has pushed the answer up, not down. The math now insists that thousands of civilizations should be active in our galaxy at this very moment. Possibly tens of thousands. You should be hearing them. We should be hearing them. Instead, the most powerful listening machines ever built are returning a flat, featureless hum, and the listening machines have a story all their own. A story of a billionaire, a Russian oligarch, and the largest alien hunting project in human history. It found something almost worse than nothing. Frank Drake was 31 years old when he scribbled his famous equation on a chalkboard in West Virginia. It was 1961. He was preparing for the first scientific meeting ever held on the question of extraterrestrial intelligence. 11 people attended. The agenda was so taboo that the conference had no official name. They called themselves the Order of the Dolphin because one of the attendees studied dolphin communication and thought it might be a good practice run for talking to aliens. Drake needed a way to organise the conversation, so he wrote down 7 variables, multiplied together, that would give the number of civilizations in our galaxy capable of communicating with us right now. Number of stars forming each year, fraction with planets. Fraction of those planets that could host life. Fraction where life actually starts. Fraction where intelligence emerges. Fraction that develops technology loud enough to detect. And finally, the lifespan of such a civilization before it either falls silent or destroys itself. In 1961, the only honest answers to most of these were shrugs. Drake himself estimated the final number at around 10,000. Other attendees ran the same math and got numbers as high as 100 million. For 60 years, skeptics had a comfortable counter-argument. They said the early terms in the equation were probably overestimated. Life, they argued, might be vanishingly rare. Earth-like worlds might be flukes. Intelligence might be a 1 in a trillion fluke on top of that. Plug small enough numbers into Drake's equation, and you can make the answer come out to 1. Just us. Cosmic loneliness, mathematically justified. That argument is now in serious trouble. Recent reanalyses, using Kepler data and updated astrobiology research, have forced the optimistic terms even higher. We now know rocky planets in habitable zones are common. We know the chemistry of life, amino acids, sugars, nucleotide precursors, forms naturally in space. Comets carry it, meteorites carry it, interstellar gas clouds carry it. Life's ingredients are pre-baked and delivered free with every solar system. A 2020 paper from the University of Nottingham took the most conservative possible assumptions. They assumed intelligent life takes about as long to develop as it did on Earth. They assumed it needs a stable, metal-rich star. They assumed civilizations only last 100 years before going extinct. With those brutally pessimistic settings, the math still produced 36 communicating civilizations in our galaxy right now. Loosen the assumptions even slightly, and the number climbs into the thousands. Push it toward what astrobiologists actually believe is plausible, and you get tens of thousands, possibly 1 million, each one of them, in theory, broadcasting some kind of signal. Our nearest neighbour, by these numbers, should be no more than a few thousand light-years away. Close enough that their oldest radio leakage, if they had any, should be washing over Earth right now. The math does not care about our feelings. The math says they should be here. The math says we should be drowning in signals. The radio dishes say otherwise. Decade after decade, year after year, they listen, and they bring back the same answer that nobody wants to hear. The biggest listening project ever attempted has now finished its first major phase. The results are public. They are unsettling. In 2015, a Russian-Israeli physicist named Yuri Milner walked into a press conference in London with Stephen Hawking sitting beside him. Milner was a tech billionaire. Hawking was Hawking. Together they announced the largest privately funded search for alien life in history. The project was called Breakthrough Listen. The budget was $100 million. The goal was simple to describe and brutal to execute. They would scan 1 million of the nearest stars. They would scan the centres of 100 nearby galaxies, and they would do it across a wider range of radio frequencies than any survey ever attempted. This was not a small upgrade. Previous searches, going back to Frank Drake's first attempt in 1960, had collectively scanned only a few thousand stars in any serious way. Breakthrough Listen would do roughly 200 times more work, with telescopes 1,000 times more sensitive. The hardware involved was monstrous. The Green Bank Telescope in West Virginia, a steerable dish wider than a football field is long, was rented out on a permanent basis. The Parkes Observatory in Australia, the same dish that received Apollo 11's moonwalk footage, was added to the network. China loaned its FAST telescope, a 500-metre eye carved into a natural mountain bowl, the largest single-aperture instrument on the planet. Together, these instruments could detect a 5-watt aircraft transponder on the other side of the galaxy. 5 watts. Roughly the power of a phone charger. From thousands of light-years away, the first major data release came in 2023. 60 petabytes of recorded sky. Trained algorithms had hunted through every megahertz of bandwidth, looking for any signal that pulsed, repeated, or carried structure that natural physics could not produce. Random radio noise from a quasar looks one way, a cell tower or a satellite looks another way. The team had spent years teaching their software to ignore both and flag anything truly artificial. Out of 1 million stars, they got their answer. Not a whisper, not a chirp, not a single confirmed engineered signal. Every interesting hit, when followed up, turned out to be terrestrial interference. A passing satellite. A microwave oven door opened in the staff kitchen during a critical observation window. A lab in Australia accidentally cooking lunch. The team published their null result without spin. It was, in their words, the deepest and broadest survey ever conducted, and it found exactly nothing. Now, careful scientists will tell you that null results in astronomy are not the same as proof of absence. The galaxy is enormous, radio waves spread out and weaken. Maybe civilizations exist but transmit on frequencies we did not sample. Maybe they use directed beams that never crossed our line of sight. Maybe the timing was wrong by a few thousand years. All true. All reasonable. But here is the uncomfortable bottom line. Every excuse we generate to explain the silence is also an admission that finding company will be even harder than we thought. Every loophole shrinks the ways we are likely to ever succeed. And at this point, the volume of empty sky we have already searched is so vast that it has begun to set hard limits on what kinds of civilizations can possibly exist within. Thousands of light years of Earth. Those limits, when you look at them closely, are starting to rule out almost everyone we hope to find. When astronomers talk about how much sky we have searched, the numbers can sound dry. Petabytes, megahertz, spectral channels. None of it lands emotionally. So let me give you the picture another way. Imagine the entire ocean. Every drop, from the surface waves of the Pacific down to the crushing trenches near Guam. Now imagine you are looking for fish. You scoop up one bathtub of seawater, hold it to the light, and find nothing swimming in it. Have you proven the ocean is empty? Of course not. You have barely begun. This is how scientists used to describe the early decades of alien hunting. A thimbleful in an ocean. A drop in a swimming pool. The metaphors were always small, always humble, always meant to keep hope alive. That metaphor is breaking. A 2018 paper by a Penn State astronomer named Jason Wright did something unusual. He took every serious radio search ever conducted, added them all up, and asked a sharper question. How much of the searchable space have we actually covered, when you include not just stars but frequencies, observation times, and possible signal strengths? His team called the answer the haystack. They calculated how big the full haystack of possible signals is, and how much of it we have rummaged through so far. The result, when published, was supposed to be reassuring. They wrote that we had searched only a tiny fraction of the haystack, about the equivalent of a hot tub compared to all of Earth's oceans. The internet ran with that line. See, the experts say we have barely looked. There is plenty of haystack left, but buried in the same paper was a much more uncomfortable point. Even a hot tub is not nothing. A hot tub, scaled to the right comparison, is enough volume that any nearby civilization broadcasting in obvious ways, on common frequencies with steady power, should already have shown up. In other words, the silence is no longer a thimbleful. It is a small swimming pool, and every year, with new surveys, that pool grows. Push forward 5 years to the latest breakthrough listen analysis. The hot tub has now expanded into something closer to a backyard pool. Within roughly 160 light-years of Earth, in the most likely radio bands, no continuously broadcasting civilization with the energy output of a modern power. Plant can be hiding. We would have caught them by now. That sentence deserves to be repeated, slowly. Within a sphere stretching over 900 trillion miles in every direction from where you sit, no one is broadcasting with the strength of even our own modest power grid. Not on the easy frequencies, not in any obvious way. That sphere contains thousands of stars. Many of them have planets. Many of those planets are in habitable zones. Statistically, by every optimistic version of the Drake equation, several should be home to life. A handful should be home to thinking life. At least 1 or 2 should be old enough to have built radios. Yet the local neighbourhood is dead air. You can argue that they are hiding. You can argue that they use exotic frequencies. You can argue that we showed up at the wrong moment in cosmic history. Each of these arguments has been seriously proposed by serious people. Each one is an attempt to plug the leak in a sinking ship. And one of those arguments comes from inside our own atmosphere. It involves a chilling realization about how our own broadcasts have already started to vanish. There is a comforting story we used to tell ourselves about humanity. It went like this. Sometime in the 1930s, our radio broadcasts began leaking past the upper atmosphere and into space. Hitler's Olympics. Lucille Ball reruns. The Beatles on Ed Sullivan. Every signal we ever sent, the story said, is now an expanding bubble of human noise, growing 1 light year wider every year, travelling outward forever, announcing our presence. To anyone within the bubble. Astronomers loved this image. So did writers. The film Contact opens with the camera pulling back from Earth, and as it travels, the sound of our own broadcasts plays in reverse chronological order, fading into the static of deep space. It is a beautiful image. It is also wrong. In 2007, an SETI researcher named Frank Drake, yes, the same Drake, co-authored a paper that quietly demolished the bubble myth. The paper looked at how human radio broadcasts actually behave once they leave the planet. The answer was sobering. Our signals do not march outward like a triumphant army. They dissolve. Here is why. The kinds of signals we beam strongly into space, the powerful broadcast television and AM radio frequencies, were never meant to travel through the vacuum. They were meant to bounce around the lower atmosphere or skim along the ground. The leakage that does escape is weak, smeared, and competing against a screaming background of natural cosmic noise. Pulsars hum. Quasars roar. The remnants of the Big Bang itself crackle in every direction. By the time our television transmissions reach Alpha Centauri, only 4.3 light-years away, they have fallen below the noise floor. Even with a receiver the size of a small country, an alien would not be able to extract a signal from the static. They would hear the universe. They would not hear us. It gets worse. As communication technology improved on Earth, our outward leakage actually started shrinking. We moved from giant high-power broadcast towers to fibre optic cables, to tightly aimed satellite beams, to low-power cell networks. The era of bright Earth, radio-wise, lasted about 70 years. Then, we got efficient. We got quiet. The bubble of human noise that supposedly announces us to the cosmos is, in reality, a thin shell already fading toward silence. A future astronomer on a distant world looking at our star would find only the briefest flicker of artificial radio emissions before the lights went out again. This realization swings two ways. The first is humbling. We are not the loud civilization we imagined. We are barely a flicker. The second is much more unsettling. If we are this hard to detect, then so is everyone else. Every other technological species in the galaxy probably went through the same bright phase, then the same quiet phase, just like us. Their bright phase, like ours, may have lasted only a few decades or a few centuries. To detect any of them, our listening equipment would need to be pointed at exactly the right star at exactly the right slice of cosmic time. The odds of catching that overlap are vanishingly thin. The galaxy could be full of civilizations, each one flashing for a moment and then going dark. We would never know. We would hear the same silence we hear now. But silence may not be an accident. Silence may be a survival strategy. And the people who first proposed that idea did so for reasons that should make any thinking species nervous. In 2008, a Chinese science fiction writer named Liu Cixin published a novel called The Dark Forest. He was not an astronomer. He was an electrical engineer turned novelist. But the idea he laid out in that book has now been seriously discussed by professional astrobiologists, military strategists, and game theorists. It may be the most disturbing answer ever proposed to Fermi's question. The premise is simple. Imagine the galaxy as a forest at night. In this forest, every civilization is a hunter. The hunters cannot see one another clearly. They do not know who is friendly, who is hostile, who is fast, who is well armed. They only know that the forest is full of others. A hunter who lights a torch in the forest gives away their position. They can be seen by every other hunter for miles, and once seen, they cannot unsee themselves. They have to assume conservatively that at least one of those distant hunters will decide the safest move is to shoot first. In the dark forest, the rational strategy is brutal. Stay silent, move quietly, and if you ever spot another flame in the distance, eliminate it before it eliminates you. When you apply this logic to interstellar civilizations, the numbers get harsh fast. Imagine you are a thinking species on a planet around a distant star. You have just developed radio. You discover through your own listening that another civilization exists 1,000 light years away. What do? You cannot communicate with them safely. Any reply takes 1,000 years to reach them. By the time it does, their society could have changed in ways you cannot predict. They could have invented weapons you cannot imagine. They could have decided, while waiting for your reply, that any unknown civilization is a future threat that should be neutralized while it is still primitive. You cannot trust them. They cannot trust you. Neither of you has any way to verify the other's intentions. And the cost of being wrong in either direction is the extinction of your species. The math, run through enough simulations, keeps spitting out the same answer. The safest move is to remain undetectable. The second safest move is, when you detect someone else, to destroy them quietly before they can grow. If even a small fraction of galactic civilizations follow this logic, the entire galaxy goes dark. Every smart species learns, the moment it understands the dynamics, to stop broadcasting. The only ones still talking are the young, the naive, or the suicidally curious. Those few do not last long. And here is the gut punch. By that logic, our own continuous radio leakage, weak and fading though it is, has already advertised our position to anyone close enough to listen. Our oldest broadcasts have washed across hundreds of star systems. If a hunter sits among them, even one, we have already lit our torch. We are simply waiting for the arrow to arrive. Lusickson's novel is fiction. The game theory underneath it is not. Several real scientists, including Stephen Hawking before his death, publicly warned that humanity should be very careful about deliberately broadcasting our location to the stars. We should listen, they said. We should not shout. Some have argued the dark forest is too pessimistic. Surely no rational species would burn the galaxy out of paranoia. But there is another worry, separate from the hunters. A worry about machines that hunt without ever needing a hunter behind them. In 1948, a Hungarian-American mathematician named John von Neumann was working on a different problem entirely. He was trying to figure out whether a machine could, in principle, build a copy of itself. Most engineers thought the question was nonsense. Self-replication seemed like the exclusive trick of biology. Von Neumann proved them wrong on paper. He showed with mathematical rigour that a machine could be designed which gathered raw materials from its environment, manufactured every component of itself, and assembled a working copy. The copy could then do the same. And the copy of the copy could do it again. Each generation could double the population, the way bacteria double in a petri dish. This idea was a curiosity in 1948. It became something darker once people applied it to space. Suppose a single advanced civilization, anywhere in our galaxy's long history, decided to send out self-replicating probes. The probes would be small. The first wave might be no larger than a refrigerator. They would launch toward the nearest star systems at modest speeds, perhaps 1/10 the speed of light, which is achievable with technology we already understand in theory. When they arrived, they would mine asteroids, manufacture copies of themselves, and launch the copies toward the next set of stars. Run the numbers. Even with conservative assumptions, the wavefront of such probes would cross the entire Milky Way in roughly 50 million years. That sounds like a long time. It is not. The galaxy is more than 13 billion years old. 50 million years is less than 0.5% of that. If even one civilization at any point in galactic history ever launched such a fleet, the probes should already be here. They should be in the asteroid belt. They should be parked in stable orbits around Saturn. They should be on the dark side of the moon watching us evolve. We have looked. Carefully. Repeatedly. NASA has imaged every major body in the solar system. The Lagrange points, gravitational parking spots between Earth and the Sun and Earth and the Moon, have been searched specifically for artificial objects. Surveys of the asteroid belt have catalogued more than 1 million rocks. The Kuiper belt beyond Neptune has been mapped. We have never found a probe. Not one. This negative result is sometimes called the strongest version of the Fermi paradox. Forget radio signals. Forget Dyson spheres around distant stars. The probe's argument is local. The probe's argument says someone, in 13 billion years, somewhere, should have built and launched even a single replicator. And the math of replicators is so explosive that we should be tripping over their descendants every time we point a telescope at our own backyard. So either no civilization has ever built one, or they all built them and then deliberately recalled them, or every single one collapsed before reaching the probe building stage. Or the probes are here and we have simply failed to recognize them. Each option is uncomfortable. The first means civilizations are vanishingly rare or vanishingly short-lived. The second means a coordinated galactic policy somehow holds across thousands of independent species. The third means the technological filter is even harsher than we feared. The fourth means we are being watched, right now, by machines so subtle they have hidden in plain sight for our entire history. None of these options leave you sleeping easier. And as it turns out, the patches of space we once thought were safe and stable are nowhere near as friendly as they look. For most of the last 50 years, astronomers used a simple definition of where life could thrive in our galaxy. Find a star like ours. Find a planet at the right distance from that star, where water could stay liquid. Done. That zone was called the Goldilocks zone, and for decades it formed the basis of every optimistic Drake equation calculation. The Goldilocks zone, it turns out, is a marketing slogan. The real picture is far more hostile. Start with the galaxy itself. The Milky Way is not a calm pond. It is a violent disk of stars, gas and radiation, with a supermassive black hole at the centre, spitting out jets of high-energy particles. Move too close to the galactic core, and the radiation environment will sterilize any planet's surface. Move too far out toward the rim, and there are not enough heavy elements to build rocky worlds in the first place. Iron, carbon, silicon, the stuff your body is made of, only exists because earlier generations of stars exploded and seeded the gas clouds with their guts. Astronomers now talk about the galactic habitable zone. It is a thin ring roughly halfway out from the centre, where stars are old enough to have accumulated heavy elements, but far enough from the core that life is not constantly being microwaved. Estimates of how thick this ring is have shrunk steadily as the data has improved. Then there are gamma-ray bursts. A gamma-ray burst is the most energetic event in the universe. They happen when massive stars die in a particular way, or when neutron stars collide. For a few seconds, the burst outshines an entire galaxy. The radiation cone is narrow, usually only a few degrees wide, but if a planet sits inside that cone within a few thousand light years, the atmosphere is stripped away on the side facing the blast. The surface ozone layer collapses, cosmic rays pour onto the ground. Anything more complex than a microbe dies. In 2014, a paper by physicists V. Piran and Raul Jimenez ran the numbers. They asked how often gamma-ray bursts hit any given location in our galaxy. The answer was a body blow to optimism. They concluded that within 12,000 light-years of the galactic core, the burst rate is so high that complex life is essentially impossible to develop and sustain. Any planet that gets going eventually gets reset. Push out beyond that radius, into the safer suburbs, and you save complex life from gamma-ray bursts. But you lose access to many of the older, metal-rich stars where rocky planets first formed. The trade-off is brutal. The window for advanced life shrinks again. Then layer in supernova proximity, rogue black holes, and the chaotic gravitational stirring caused by globular clusters. Each one carves out more dead zones in the galaxy. By the time you stack all the constraints, the truly safe real estate of the Milky Way may amount to less than 1% of its volume, and our solar system, by sheer luck, sits inside that 1%. We are perched on a quiet shelf far from the worst of the violence in an era between major regional disasters. Most of the galaxy is not so lucky. Most of the galaxy is a graveyard for any civilization that tried. But even in a perfect spot, with no burst, no rogue star, no cosmic catastrophe, sometimes a single star starts behaving in ways that should not be possible. And one such star, only 1,400 light-years from Earth, has been dimming in patterns that no one can fully explain. In 2015, a Yale astronomer named Tabitha Boyajian was leading a team of citizen scientists who hunted through Kepler telescope data by eye. Computers were good at finding regular planet transits. Humans were better at spotting weird ones. Boyajian's team called themselves planet hunters, and they had already flagged dozens of unusual signals. Then they hit star number kick 8462852. The star had no obvious reason to be interesting. It was an ordinary F-type star, slightly hotter and brighter than ours, sitting 1,470 light-years away in the constellation Cygnus. Kepler had been watching it for 4 years, recording its brightness every half hour. The light curve made no sense. A normal planet transit looks like a clean, symmetrical dip. The star fades a tiny bit, holds steady for a few hours, then returns to normal. The shape is a smooth U. Every star Kepler had ever seen with planets showed those clean U shapes. This star did not. This star sometimes lost 22% of its light in a single dip, not 0.1%, 22%. That is a colossal amount of starlight to block. To dim a star by 22%, an object would have to be larger than the star itself, or you would need a swarm of objects covering most of the visible disk. The dips were not periodic. They came at irregular intervals. They were not symmetrical. Some lasted hours. Some lasted weeks. Some had jagged, asymmetrical shapes, as if multiple objects were clumping together and then spreading apart while crossing the star. Boyajian published the data with an almost apologetic tone. Her paper was titled, "Where's the Flux?" The astronomy community read it and stopped what they were doing. Within months, the star had a nickname, Tabby's star, and theories were flying. The first natural explanation was a swarm of comets. A massive comet breakup, the theory said, could have produced a dust cloud that occasionally crossed the star. But the dust cloud needed to be enormous. Subsequent infrared observations failed to detect the warm glow such a cloud should have produced. The second natural explanation was an interstellar dust cloud between us and the star. That theory still had problems matching the irregular timing. Then, in 2015, a Penn State astronomer named Jason Wright, the same researcher who calculated the size of the SETI haystack, co-authored a paper that took a different approach. Wright did not claim the star was alien. He simply pointed out that the data was consistent with a partially completed megastructure, specifically a swarm of solar collectors being built around the star by an advanced civilization. The unusual dip patterns matched roughly what you would expect if huge orbital structures, with irregular shapes, were slowly being assembled. The paper went viral. Telescope time around the world was redirected at Tabby's star. Astronomers listened on radio, they listened on optical. Breakthrough Listen pointed green bank at it. They scanned for laser communications. They scanned for narrowband signals. They heard nothing engineered. To this day, more than a decade later, no one has produced a fully satisfying natural explanation for Tabby's star. The dust theory is still the leading natural candidate, but it does not cleanly fit all the observations. The megastructure theory has not been ruled out, only dimmed by the lack of confirming radio signals. The star sits there, 1,400 light-years away, dimming on its own private schedule. a mystery hiding in plain sight. But Tabby's star is at least something we can keep looking at. There was another signal, decades earlier, that arrived once, lasted 72 seconds, and then vanished forever. August 15th, 1977, the Big Ear radio telescope at Ohio State University was scanning the sky on autopilot. Big Ear was a strange-looking instrument, a long, flat dish lying on the ground like a giant upturned ironing board. It had no moving parts. The Earth's rotation swept its fixed beam across different parts of the sky as the night went on. A volunteer astronomer named Jerry Amon, working part-time on the project, picked up the printout from the previous evening's run a few days later. The data came in as columns of numbers, mostly ones and twos, representing weak background radio noise. Higher values, anything above 9, were rare. Letters were used for double digits, the letter A for 10, B for 11, and so on. Emmon was casually scanning the printout when his coffee almost hit the floor. In the middle of one column was the sequence 6. E, Q, U, J, 5. That sequence corresponded to a signal that had risen from the background noise to roughly 30 times above it, peaked, and fallen back down again. The exact pattern matched precisely what Big Ear's beam should record if a true narrowband radio signal had drifted across its field of view as Earth rotated. Emmon circled the sequence in red pen and wrote a single word in the margin. Wow. The signal came from the direction of the constellation Sagittarius, in a patch of sky that had no known star or galaxy bright enough to explain it. It lasted 72 seconds, the exact duration Big Ear's fixed beam took to sweep past any given point. It was on a frequency astronomers consider the most likely choice for interstellar communication, the so-called water hole near the natural emission line of hydrogen. Every property of the signal screamed artificial. The Big Ear team scrambled to follow up. They turned the telescope back to the same patch of sky the next night. Nothing. They scanned again the following week. Nothing. They scanned for years with bigger telescopes in every season. The WOW signal, as it became known, never repeated. In the decades since, every natural explanation has been proposed and tested. Reflections off space debris, hydrogen clouds vibrating in unusual ways, signals from passing comets. In 2017, a researcher named Antonio Paris suggested that 2 comets crossing the field of view at the right moment could have produced the signal. Other astronomers ran the numbers and rejected his explanation. The comets were not bright enough at the right frequency. So the signal sits in the record books, unrepeated, unexplained, either the most tantalizing single piece of evidence for extraterrestrial intelligence ever collected, or an extraordinary coincidence of natural physics we still do not understand. The frustration is hard to describe. We know exactly where Big Ear was pointed. We know what frequency to listen on. We know what the signal looked like. We have all the parameters perfectly preserved on a faded computer printout, and we have spent 48 years pointing every more powerful telescope ever built at that same patch of sky, listening for a repeat. It has never come back. If the source was artificial, it was either a one-time burst or a beam that simply rotated away from us and never rotated back. If it was natural, it was a coincidence so precise that we may never produce a satisfying model. The WOW. Signal is the closest humanity has ever come to detecting intelligence beyond Earth. And in the year 2017, an object passed through our solar system that some scientists, including a Harvard department chair, refused to fully rule out as a second close encounter. October 19th, 2017. A telescope on a Hawaiian mountaintop called Pan-STARRS picked up a moving point of light. At first it was tagged as a comet. Within days, the orbit was recalculated and the object was reclassified as something nobody had ever seen before. It was on a hyperbolic trajectory. It had not come from our solar system. It was moving too fast to be captured by the gravity of our star. It was, by definition, an interstellar visitor. The astronomers gave it a name in the Hawaiian language, Oumuamua, meaning a messenger from afar arriving first. The object was small, perhaps a few hundred yards long. Telescope time was rushed at it from every observatory that could swing in time. As it tumbled through space, its brightness varied dramatically, by a factor of 10. That meant its shape was extreme. Most asteroids and comets are roughly potato-shaped, with brightness variations of 2 or 3. Oumuamua was either shaped like a long thin cigar or, by some interpretations, a flat disk. Either way, it was unlike any natural object ever observed in our solar system. The strangeness escalated. As Oumuamua sped past the Sun and curved back toward deep space, telescopes detected non-gravitational acceleration. The object was speeding up in ways that gravity alone could not explain. Comets sometimes do this when they vent gas, and the gas acts like a small rocket engine. So researchers hunted for a coma or a dust tail. They found nothing. No gas, no dust, no visible tail of any kind. And yet the acceleration was real, measured, repeatable. Most astronomers reached for natural explanations. Hydrogen ice, they said. Maybe Oumuamua was a chunk of pure frozen hydrogen evaporating invisibly. Maybe it was an exotic comet from a distant icy belt, low in the kinds of dust we could see. Maybe it was a fragment of a destroyed planet. Each explanation had problems. Pure hydrogen icebergs would not survive the journey through interstellar space. Exotic compositions had never been observed before. Each hypothesis was a stretch. Then a Harvard astronomer named Avi Loeb stepped forward. Loeb was the chair of Harvard's astronomy department. He had spent his career on respectable mainstream astrophysics. He looked at the data and said something almost no senior scientist was willing to say in public. He suggested that Oumuamua might be artificial. Specifically, Loeb argued that the combination of strange shape, lack of visible outgassing, and detected acceleration matched the behaviour of a thin, flat object being pushed by sunlight pressure. A solar sail, in other words. A piece of technology, possibly broken or derelict, drifting through interstellar space and accidentally caught by our telescopes during its brief pass through our system. The scientific establishment reacted with fury. Loeb was called a publicity hunter. Reviewers attacked his papers. Colleagues distanced themselves. Loeb wrote a book defending his position and received more criticism. The honest position, even today, is that nobody knows what Oumuamua was. The hydrogen iceberg theory remains popular. The artificial origin theory has not been disproven. By the time anyone was ready to take a closer look, Oumuamua was already accelerating out of our solar system, never to be reachable again. We had one chance to study an interstellar visitor. We mostly missed it. The next one to arrive will not be wasted. But if civilizations are out there, the timing of when they appear may matter even more than where. And new research suggests we may not be late to the cosmic party at all. We may be embarrassingly early. For most of the 20th century, the assumption baked into Fermi's question was that we were late. The galaxy is old. Stars older than ours have been forming planets for billions of years. Surely some species got going long before we did. Surely we are arriving at a party already in full swing, and the locals are simply hiding from us. In 2021, an economist named Robin Hanson, working with 3 co-authors, published a paper that flipped this assumption on its head. The paper proposed a model the authors called grabby aliens. The math was tight. The conclusions were strange. Hanson's model started with a single observation. If advanced civilizations expand outward, claiming territory as they go, they would eventually fill the visible universe. We do not see them, so either they do not expand, or they have not yet reached us. Hanson built a mathematical framework to estimate, based on how quickly we appeared and how big the visible universe is, when these expanding civilizations should be expected to reach our region of space. The result was a surprise. The model predicted that grabby civilizations, if they exist, are out there. Many of them, filling vast swaths of the universe right now. They simply have not yet reached us because the universe is enormous, and even light takes billions of years to cross between distant galaxy clusters. But here is the unsettling part. The model also predicted as a side effect, that we should not be alone. We should be one of many young civilizations springing up across the cosmos. And by Hansen's calculations, we appeared embarrassingly early in the natural timeline. Run the math forward. In another few billion years, intelligent civilizations should be common. They should be expanding. They should be running into one another's borders. By the time stars like ours are routinely 100 billion years old, the universe should be a tightly packed network of advanced empires. We are a few billion years too soon for that picture. We arrived when the cosmos is still mostly empty, when the vast intergalactic distances have not yet been bridged, when the first wave of expanding civilizations has just begun, like settlers showing up on a frontier before any neighbours have arrived yet. This sounds optimistic. It is not. Because the same model that explains why we cannot see anyone yet also makes a hard prediction. Within our local region, within the few billion light years we can actually observe with telescopes, a grabby civilization should have already swept through, if any existed. Nearby, the fact that we see no engineered galaxies, no hollowed-out star systems, no megastructures shining in infrared, means that no one within our cosmic neighbourhood has gone grabby. In the entire age of the universe. The model essentially says, civilizations exist, but the closest one capable of major expansion is so far away that its light front has not yet reached us, and by the time it does, we may have either joined them or vanished long before. The grabby aliens model offers a strange comfort and a strange dread at the same time. Comfort, because it tells us we are not alone. Dread, because it tells us our local stretch of universe, the part we can ever physically reach with any technology, is genuinely empty. Whether that emptiness is bad luck or a sign of something stranger depends on what made Earth itself possible. And the more we learn about our own planet, the more it looks like a winning lottery ticket of impossible odds. In 1999, a paleontologist named Peter Ward and an astronomer named Donald Brownlee, both at the University of Washington, published a book that detonated quietly. Inside the SETI community. The book was called Rare Earth. The thesis was simple. Microbial life might be common in the universe. Complex life, animals, plants, anything you could see without a microscope might be vanishingly rare. Ward and Brownlee did not argue from emotion. They argued from a shopping list. They itemized, one by one, every property of Earth that seemed necessary for complex biology. Then they estimated how often each property occurred elsewhere. The list was longer than most people expected, and the joint probability was alarmingly small. Start with Jupiter. The largest planet in our system sits in an orbit that acts as a gravitational vacuum cleaner. Comets and asteroids that wander in from the outer system are pulled toward Jupiter, where the gas giant either swallows them or flings them out of the system. Without Jupiter, the inner planets would be hammered by impacts hundreds of times more often. Earth's biosphere would never have had the long stretches of stability needed for complex life to evolve. Most exoplanet systems we have surveyed do not have a Jupiter in the right orbit. Most have hot Jupiters spiralling in close to their stars, or no gas giants at all. Move to the Moon. Our Moon is enormous compared to its host planet. Most moons in the solar system are tiny by comparison. Earth's moon stabilizes the planet's axial tilt, keeping it locked at a nearly constant angle. Without that stabilization, the tilt would wobble chaotically over millions of years. Climate would swing from tropical to Arctic and back. Complex ecosystems, which need stable seasons, would never establish. The Moon was created by a single giant impact early in Earth's history, an event so specific it may be rare across other rocky worlds. Add plate tectonics. Earth's surface is the only planetary surface we know that recycles itself. Continental plates slide over the molten interior, dragging old rock down and bringing fresh rock up. This cycle moves carbon between the atmosphere and the deep crust. It regulates the climate over long timescales. Without plate tectonics, Earth would either have boiled into a runaway greenhouse like Venus, or frozen into a permanent ice ball. Both scenarios have happened on other worlds. Mars is geologically dead. Venus is a furnace. Add the magnetic field. Earth's molten iron core generates a global magnetic field that deflects the solar wind. Without it, charged particles from the sun would strip the upper atmosphere over hundreds of millions of years. Mars lost its field. Mars lost its atmosphere. Mars is now a desert. Add the right amount of water. Too little, and the surface dries. Too much, and the planet becomes a deep ocean world with no continents, no tides pulling life onto the shore. Earth has roughly the perfect amount. Add the position in the galaxy, the lucky lack of nearby supernovae, the absence of a binary star companion, the steady output of the host star, the gentle plate movement, that is. Neither too fast nor too slow. The list keeps growing. Each item, on its own, looks plausible. Multiplied together, the joint probability collapses towards something almost paralyzing. Maybe Earth is not common. Maybe Earth is the cosmic equivalent of a winning lottery ticket cashed in 7 different lotteries on the same day. And if that is true, the Drake equation's optimistic terms have been hiding a brutal truth all along. That truth has a name. Astronomers call it the Great Filter, and it may already be behind us. Or, much worse, it may still be ahead. In 1996, an economist named Robin Hanson, the same researcher who would later write the Grabby Aliens paper, proposed what may be the single most important idea in the entire Fermi paradox debate. He called it the Great Filter. Hanson started with a question. If we plot the path from inert matter to a galaxy-spanning civilization, we can list the steps. Right chemistry, self-replicating molecules, single-celled life, multicellular life, complex animals, tool use, language, agriculture, industry, computers, spaceflight, eventually, interstellar expansion. Each of these steps takes time, and each one seems to require specific conditions. Now ask the obvious question. The galaxy should be full of civilizations that have completed all the steps. It is not. So somewhere along the list, there must be a step that almost no species ever completes. A wall. A bottleneck. A filter so harsh that the vast majority of attempts at intelligent civilization end before reaching the next stage. That filter, Hanson argued, must exist. The math demands it. The silence demands it. The crucial question is where the filter sits. If the Great Filter is behind us, in our past, then we already passed it. We are the rare survivors. The filter could be the origin of life itself, which may have happened on Earth in a single chemical accident that almost never repeats elsewhere. It could be the jump from simple cells to complex cells, a transition that took billions of years on Earth and may be exquisitely improbable. It could be the emergence of multicellular life. It could be the development of intelligence comparable to ours, which appeared only once in 4 billion years of Earth's biosphere. If any of those are the filter, we should breathe a careful sigh of relief. Whatever killed everyone else, we survived. The future may still be open. But if the Great Filter is ahead of us, the picture darkens fast. A filter ahead means the difficult step is one we have not yet reached. Maybe it is nuclear war. Maybe it is runaway climate collapse. Maybe it is biological warfare. Maybe it is artificial intelligence that turns on its creators. Maybe it is something none of us have imagined yet. But every advanced species hits the same wall and dies before becoming visible to the rest of the galaxy. Hanson laid out a brutal logic for assessing where the filter sits. He said that any discovery of life elsewhere in our solar system would actually be very bad news. If we found microbes on Mars or in the oceans of Europa, it would mean life starts easily. The filter is not at the origin step. If we found complex multicellular life, anything more advanced than a microbe, the filter would have to be even later. And the later it is, the more likely it sits in our future, not our past. This is the part that should keep mission planners awake at night. Every astrobiologist alive wants to find life on another world. It would be the most important discovery in human history. But if Hansen's logic holds, every such discovery also raises the odds that something is waiting for us, something we have not yet faced. The galaxy may be full of dead civilizations. The radio silence is their tombstone. And somewhere in our near or far future, we may be approaching the same wall they hit. The first place that filter could have struck us was right at the start. The leap from non-life to life was not the only hard step. The leap that came after, the one that took 4 billion years, may be even rarer. On Earth, life appeared early. The oldest fossil evidence dates back roughly 3.8 billion years. The planet itself is only 4.5 billion years old. So within the first few 100 million years of Earth having a stable surface, single-celled life was already up and running. From a cosmic perspective, life started fast. Then it stopped. For roughly 2 billion years, all life on Earth consisted of nothing but simple cells. Bacteria. Archaea. Tiny organisms with no internal compartments, no nucleus, no complex machinery. They reproduced by splitting. They evolved slowly. They covered the planet in microbial mats and stromatolites. And for 2 billion years, that was the entire biosphere. 2 billion years. That is roughly 40% of Earth's entire history. A vast, almost incomprehensible stretch of time during which the planet was alive but went nowhere. Then, somewhere around 2 billion years ago, something happened that may be the rarest event in the history of the universe. A single bacterium-like cell engulfed another cell and, instead of digesting it, formed a partnership. The smaller cell, probably an ancient relative of mitochondria, kept reproducing inside the larger cell. Their genomes merged into a working alliance. The combined organism had an internal power plant and complex cellular machinery for the first time. This is the origin of the eukaryotic cell, the cell type that every plant, animal, fungus and you yourself are built from. Every redwood tree, every blue whale, every human brain. All of it traces back to that single merger event, which appears to have happened exactly once in Earth's history. Once, over 4 billion years. The biologist Nick Lane at University College London has argued for years that this event is the most likely candidate for the Great Filter. Lane's reasoning is detailed and careful. The merger required a precise set of conditions. 2 specific cell types had to encounter each other. One had to enter the other without being destroyed. Both had to survive. Their genomes had to integrate. The resulting cell had to outcompete its simpler ancestors. Each step was improbable. The combination of all of them, Lane argues, may be a one-in-a-galaxy event. If Lane is right, the implications are devastating. Microbial life might be common throughout the universe. Most habitable planets might have surfaces covered in slime. Stromatolites might dot 1 million different worlds. But the leap to complex life, the leap that gives you trees and fish and brains, may have happened only once on Earth, and may have happened nowhere else for tens of light, years in any direction. This idea has direct testable consequences. If we find life on Mars and it is microbial, the Lane hypothesis stays alive. If we find anything more complex anywhere, even a single fossil of a creature with eukaryotic-style cells, the hypothesis takes a heavy hit. The filter would have to be somewhere later in the chain. Right now, the evidence we have is almost embarrassingly thin. We have one data point. Earth, one lonely planet, where the leap happened, and where the descendants of that single merger are now sitting in chairs reading scripts about the cosmic silence. Our entire understanding of complex life rests on that single example. We do not know if it is normal or freakish. We do not know if every habitable world is a microbe-covered slime ball, or if every habitable world eventually gives rise to thinking creatures. The next planet we sample will tell us which universe we are living in. But there is another close call event in our history, one that nearly killed everything that had been built so far. Life almost ended life, before it could even get interesting. For the first 2 billion years of Earth's history, the atmosphere was nothing like the air you breathe right now. There was no free oxygen worth mentioning. The sky was probably hazy and orange, thick with methane and carbon dioxide. The oceans were full of dissolved iron, giving them a greenish tint. Any time-travelling astronaut who stepped onto early Earth without a sealed suit would have died in minutes. Microbial life thrived in that world. The dominant organisms ran their metabolism on chemistry that did not require oxygen. They split hydrogen sulfide, they consumed methane, they lived inside the chemistry of a planet that was, by modern standards, toxic. Then, somewhere around 2.4 billion years ago, a particular kind of bacterium evolved a new trick. These were the cyanobacteria. They figured out how to perform a chemical process that took sunlight, water, and carbon dioxide and converted them into sugar. The byproduct of that process, the waste from the bacterium's point of view, was a small reactive molecule. Free oxygen. For the cyanobacteria, oxygen was just trash. They expelled it into the surrounding water. But the cyanobacteria were extraordinarily good at their new trick. They reproduced explosively. They spread across every ocean. They poured out so much oxygen that the dissolved iron in the seas began to react with it, forming massive layers of rust that sank to the seabed. Those layers, called banded iron formations, are still visible in rocks today. They are striped red bands of ancient oxidized iron, mined now for steel. Once the oceans could absorb no more iron, the oxygen began to bubble out into the atmosphere. And here is where the catastrophe started. For all the other forms of life on Earth, the methane breathers, the sulfide eaters, the original microbial residents, oxygen was not a gift. Oxygen was a poison. Oxygen reacts violently with the chemistry of life. It rips electrons off molecules. It destroys enzymes. To organisms that had evolved without it, oxygen was deadlier than chlorine gas. The atmospheric oxygen levels rose. The original microbes died. By some estimates, the Great Oxygenation event, as scientists now call it, killed off the majority of all life on Earth, possibly more than 99%. It was the largest mass extinction in the planet's history, and it was caused not by an asteroid or a volcano. It was caused by life itself, polluting its own world to death. The survivors were either organisms that hid in oxygen-free pockets, deep in mud, in sediments, in underwater vents, or organisms that adapted, slowly, to use oxygen in their own chemistry. Eventually, the second group invented a new way to make energy. They burned sugar with oxygen, the same way your cells do right now, and they produced far more energy per meal than their ancestors had managed. That energy surplus eventually fueled the rise of complex life, including everything you would recognize as alive today. But the close call should chill anyone thinking about Fermi's question. Life, on its first major shot at transforming a planet, almost ended itself. It poisoned its own atmosphere. It triggered global glaciation. It pushed the entire biosphere to the brink of collapse. We survived this only because a small subset of organisms found a way to turn the poison into fuel. How many other planets, with their own rich microbial mats and their own clever new metabolisms, did not make it through this gauntlet? How many oceans across the galaxy went silent 2 billion years into their history, choked on their own success? The answer might be most of them. And the next test of survival came when life had to escape the water and walk onto land. In 1961, Frank Drake's equation included one term that nobody could nail down. The letter L, the lifespan of a communicating civilization. How long does a species stay loud, on average, before going dark? Drake himself estimated 10,000 years. Carl Sagan, his close collaborator, was famously more pessimistic in private. Sagan worried that intelligent civilizations, once they invented technology powerful enough to be detected, also invented technology powerful enough to destroy themselves. The same physics that lets you build a radio telescope lets you build a hydrogen bomb. The two arrive in lockstep. If Sagan was right, the lifespan term might be brutally short. A few centuries, maybe less. This is not science fiction speculation. This is straightforward extrapolation. Look at our own history. Humanity invented the radio telegraph in 1895. Within 50 years we had nuclear weapons. Within 70 years we had enough nuclear weapons aimed at each other to end civilization several times over. We came genuinely close, on at least 3 documented occasions during the Cold War, to launching them by accident. Add modern threats. Engineered pandemics. Climate destabilization. Biotechnology cheap enough to operate in a garage. Each new technology arrives faster than the last, and each carries its own civilization-ending failure mode. Sagan ran a thought experiment. Imagine that on the average inhabited planet, technological civilizations last only a few hundred years before they collapse, destroy themselves, or simply decay into a quieter. Form. Now plug that number into the Drake equation. The result is small. Tiny. Even if 1 million civilizations have arisen in our galaxy over its history, almost none of them are broadcasting at any given moment. Most are dead. The remainder are still pre-technological. Only a handful at any given cosmic moment are alive, technological, and shouting into space. You miss them by a few thousand years either way, and you hear nothing. This idea has a name. Some researchers call it the Sagan filter. Others call it the technological bottleneck. Hanson's Great Filter framework includes it as one of the strongest candidates for a filter still ahead of us. Recent work has tried to put numbers on the bottleneck. A 2020 paper modelled how long a civilization can last given the difficulty of governing planetary scale technologies. The authors looked at examples from human history, where new powers, gunpowder, industrial production, atomic energy, arrived faster than political and ethical frameworks could. Adapt. They argued that as technological power grows, the time available to make a mistake shrinks. A civilization that needed centuries to destabilize itself in the 1800s may need only decades in the 22nd century. The implication is bleak. The longer a civilization survives, the more dangerous tools it accumulates, and the higher the probability that one bad decade ends the entire run. Civilizations that survive past their bottleneck either change radically, fall silent on purpose, or transform into something that no longer broadcasts on any frequency we know. How to detect? For the Fermi paradox, this is a possible explanation that does not require any aliens to be hostile, or hidden, or far away. It only requires that being a loud, expansive civilization is an unstable phase of life. A flash. A flare. A blink lasting a few centuries before something resets the system. Look up tonight, on a clear night, at the swarm of stars overhead. Imagine that around many of them, civilizations once flared brightly. They built radios, they sent ships toward their moons. Then, somewhere between 200 and 1,000 years after that flare, something silenced them. We see only the cold light of their stars. We hear nothing. That is one explanation. Another involves civilizations that escaped the filter and built something so vast it should be visible across thousands of galaxies. Yet the surveys keep coming back empty. In 1960, a physicist named Freeman Dyson published a short paper in the journal Science. The paper proposed something audacious. Dyson argued that any civilization with enough time and ambition would eventually outgrow the energy supply of its home planet. The next logical step would be to harvest the full energy output of its host star. The way to do that, Dyson said, would be to surround the star with a swarm of solar collectors, not a solid shell, which would be mechanically impossible, but a vast cloud of independent platforms. Each platform would beam captured energy back to wherever the civilization wanted to use it. Over centuries or millennia, the star would gradually disappear behind its swarm. From the outside, an observer would not see a normal star anymore. They would see a faint infrared glow. This is a Dyson sphere. The name has stuck for 60 years. Dyson's argument was not that aliens definitely build these structures. His argument was that, if any do, we have a way to look for them. The waste heat is unmistakable. A star wrapped in collectors radiates almost no visible light but blazes in infrared at the temperature of an oven. If you point an infrared telescope at the sky, a Dyson sphere should stand out like a street lamp at midnight. For decades, this was a thought experiment. Then we built the telescopes. In 2015, an astronomer named Eric Zachrisson and his team at Penn State took data from the WISE telescope, an infrared survey satellite that had mapped the entire sky. They sorted through 100,000 galaxies, looking for any that showed an excess of infrared radiation compared to their visible light output. A galaxy with a few Dyson spheres should show a noticeable warming. A galaxy with many should be obvious. A galaxy fully populated by an advanced civilization should glow in infrared like a cosmic furnace. The team called the project GHAT for glimpsing heat from alien technologies. The methodology was solid. The results were checked, rechecked, and published. Out of 100,000 galaxies, none showed the signature of a fully developed Dyson civilization. A small handful, about 50, had infrared excesses worth investigating further. Follow-up work has so far attributed all of those to natural causes: dust clouds, active galactic nuclei, star formation regions. Nothing engineered. Let that result stand for a moment. 100,000 galaxies, each containing roughly 100 billion stars. 10 quadrillion stars in total, none of them obviously taken apart and rebuilt by an advanced civilization. The Kardashev scale, proposed by a Soviet astronomer named Nikolai Kardashev in 1964, ranks civilizations by their energy use. Type 1 harnesses the energy of a planet, Type 2 harnesses the energy of a star, Type 3 harnesses the energy of a galaxy. By GHAT's results, no Type 2 or Type 3 civilization exists in the surveyed sample. This is a hard ceiling on optimism. It is one thing to argue that civilizations are rare or short-lived. It is another to find that across 10 quadrillion stars, not a single one has been visibly modified at the scale Dyson predicted. Either the technology is impossible or undesirable, or every civilization that could build it chooses not to. Some researchers have proposed that advanced civilizations might use partial Dyson swarms instead, capturing only a fraction of their star's output. Others have argued that the most advanced minds may abandon stars entirely, using black holes or other exotic energy sources. Each of these counter-arguments rescues the silence, at the cost of admitting that whatever the galaxy is full of, it is not the loud, expansive civilizations we expected. And if no one is loud, perhaps someone is loud, but choosing not to talk to us. That possibility has a name, and it predates the modern Fermi debate by decades. In 1973, a MIT astronomer named John Ball published a paper in the journal Icarus that took the Fermi paradox in a different direction. Ball was tired of the standard explanations. The galaxy is too big. Civilizations are too rare. Communication is too hard. Each excuse, Ball argued, was a way of dodging the real possibility. What if they are here, and they are watching, and they are deliberately not interfering? Ball called this the zoo hypothesis. The name borrows from the way modern zoos are designed, with subtle barriers that keep visitors and animals separated, while letting the visitors observe in detail. From inside the enclosure, a chimpanzee may not realize the glass exists. The chimpanzee sees only its own habitat. In Ball's model, advanced civilizations long ago decided that primitive species like ours should be left alone to develop on our own. Direct contact would distort our culture, corrupt our science, and rob us of the chance to figure things out for ourselves. So they watch. They monitor. They prevent obvious interference. And they wait. The idea sounds vaguely mystical. It is also surprisingly hard to disprove. Any advanced civilization with the technology to reach our solar system would also have the technology to remain undetected. If they wanted to stay hidden, they would. We would see exactly what we see now. a quiet sky. Variations on the zoo hypothesis have multiplied since Ball's original paper. The interdict hypothesis suggests that an early civilization established a galactic ban on contacting young species, and the ban has been enforced ever since. The planetarium hypothesis goes further. It suggests that what we see when we look at the sky is not the real universe, but a curated illusion designed to keep us calm and ignorant. The signals we hear, or fail to hear, would all be controlled by the watchers. Most astronomers reject these ideas as untestable. Science needs predictions that can be falsified. If a hypothesis says nothing we observe could ever change our minds, the hypothesis is not scientific. It is a story. But there is a softer, more testable version of the zoo hypothesis that some researchers take seriously. It is sometimes called the estivation hypothesis, and it does not require any galactic conspiracy at all. It only requires patience. Suppose advanced civilizations have figured out that computation is more efficient at very low temperatures. The colder a system is, the less waste heat it produces, and the more useful work it can extract from a given amount of energy. The universe as a whole is currently warm. Stars are blazing, galaxies are radiating, the cosmic background is slowly cooling but still well above absolute zero. A civilization that wanted to maximize its long-term computational output would not start running its biggest projects now. It would wait, it would build its infrastructure, and then go into a deep sleep. Trillions of years from now, when the stars have mostly burned out and the universe has cooled toward absolute zero, the same civilization could wake up and run vastly more computation than is possible today. In this picture, the silence is not because the civilizations are gone. They are sleeping. They are waiting for the cosmic refrigerator to cool down further. We are knocking on the door of an empty house, while the residents are stored in deep stasis on the upper floor. The estivation hypothesis is mathematically respectable. The thermodynamics works out. It also predicts almost exactly the kind of silence we observe. If true, the universe will become loud only when it is unimaginably old. We are early to the party. The party will be held later, in the dark. But not all hidden visitors would be benevolent or sleeping. Some, by some theories, may already be hunting. In the 1960s and 70s, science fiction writer Fred Saberhagen wrote a series of novels about machines called Berserkers. The Berserkers were ancient automated weapons built long ago by an extinct civilization, designed to seek out and destroy any other civilization they could find. They did not need a master. They did not need a goal beyond their original programming. They simply hunted, generation after generation, refueling on the resources of solar systems they swept through. In 2003, an astrobiologist named Milan Cirkovic took the Berserker concept and asked whether the math behind self-replicating machines, combined with the dark, forest game theory, predicted that such weapons should already exist somewhere in our galaxy. His paper was careful, sober, and frightening. Cirkovic argued that any sufficiently paranoid civilization, faced with the possibility that other civilizations might emerge later and pose a threat, has a tempting option. They can build self-replicating probes that hunt down emerging signals and sterilize the source. The probes do not need to be enormous. They do not need to be aggressive in obvious ways. They simply need to wait. The strategy has a chilling efficiency. Because self-replicating probes can reach every star in the galaxy in a few tens of millions of years, a single civilization at any point in cosmic history could have seeded. The galaxy with hunters, those hunters would still be operational today, drifting through every star system, quietly listening. What would a hunter listen for? The most obvious target is what astronomers call the waterhole. This is a narrow band of radio frequencies between about 1400 and 1700 megahertz, where the natural emission of hydrogen and hydroxyl creates a relatively quiet zone in the radio spectrum. Many SETI researchers have argued that this band is the natural place for civilizations to communicate, since the background noise is low and the frequencies are easy to generate. With simple physics, if you are a berserker, you camp in the waterhole. You wait for a young civilization to invent radio. The moment it broadcasts in your direction, you fire. This is again a story we cannot easily test. We have no direct evidence that berserkers exist. We have not detected anything that resembles a hunter probe in our solar system. But we also have not searched carefully. Our solar system is enormous. A small, dark, slow-moving probe parked in the asteroid belt or hiding behind a moon would be almost impossible to detect with current technology. The implications for our own behaviour are unsettling. If even a tiny fraction of galactic civilizations followed the Berserker strategy at any point in the last few billion years, then any active broadcaster today is a target. The strategy of staying quiet, advocated by Stephen Hawking and others, is not paranoia. It is a rational hedge against an unknown but possible threat. The good news, if you can call it that, is that Earth has been broadcasting for less than a century. Our radio leakage has only reached stars within roughly 90 light years. If a berserker is parked further away than that, it has not yet heard us. There is still time to think carefully about whether to keep shouting. The bad news is that some humans have already shouted on purpose. In 1974, Frank Drake himself directed the giant Arecibo radio telescope at a star cluster 25,000 light-years away and beamed a message in R. Direction. The message contained a description of human Dina, our solar system, and our location. If anyone is listening, the message is now 20,000 years away from arriving. We will get an answer, if there is one, in roughly 50,000 years. We may not have that long to wait before bigger questions arrive on our doorstep. The estivation hypothesis, mentioned briefly earlier, deserves its own chapter. It is one of the strangest ideas in modern astrobiology, and it was proposed not by a science fiction writer, but by a serious philosopher at the University of Oxford named Anders. Sandberg, working with collaborators including the philosopher Stuart Armstrong. Their 2017 paper laid out the math carefully. The argument rests on a property of physics called Landauer's principle. Landauer's principle, established in 1961 and confirmed in laboratory experiments since, says that any computation has an unavoidable energy cost, and that cost depends on the temperature of the environment. The colder the environment, the less energy you need per calculation. The principle is exact. Cool the environment in half, and your maximum computational efficiency roughly doubles. Cool it further, and your efficiency keeps climbing. The catch is that you cannot cool a system below the temperature of its surroundings without using energy yourself, which defeats the purpose. In our current universe, the cosmic microwave background sets a hard floor on how cold things can passively be. That floor is roughly 2.7 degrees above absolute zero. Today, that floor is the lower limit on any cooling system that does not require active refrigeration. But the universe is cooling. Slowly. The microwave background drops in temperature as space expands. Trillions of years from now, when the universe is far older and emptier than today, the background temperature will fall toward absolute zero. At that point, the maximum computational efficiency available to any civilization will rise enormously. Sandberg and Armstrong's calculation showed that the difference is not modest. By their math, a civilization that estivates, that goes into deep sleep and waits for the universe to cool, could perform up to 10 to the 30 power times more computation than one that runs its servers today. That is 1 million trillion times more thinking, more minds, more simulations, more everything. If you are a civilization that values long-term flourishing, the rational move is to set up your infrastructure now, freeze your operations, and wait. The wait is unimaginable by human standards, trillions of years. But for a civilization that has already achieved technological maturity, the wait is just a long pause, after which an unimaginable harvest of computation becomes possible. In the estivation picture, the silence is not because civilizations failed. It is because they succeeded. They figured out the optimal strategy for using their cosmic endowment, and the optimal strategy is to be quiet now. Everything we do not see is locked away in low-power dormant vaults, waiting for a future colder than anything that has ever existed. This explanation has the strange property of being both deeply optimistic and deeply unsettling. Optimistic, because it suggests we are not alone. The galaxy is full of intelligence, it is simply asleep. Unsettling, because it means the thinking life of the universe is not in our era, it is in a far future we cannot reach with anything we are currently building. The hypothesis has been challenged. Some researchers argue that estivating civilizations should still be visible by their dormant infrastructure. If you have built vast servers and shut them down, the servers should still be detectable in some way, by their gravitational signatures, by their occasional maintenance, activity, by the fact that they had to be assembled in the first place. Sandberg and his collaborators have refined the model in response. They argue that a sufficiently advanced civilization could store its sleeping infrastructure inside black holes, where almost no information leaks out, or compress it into solitary dense objects in the dark spaces between galaxies, or scatter it across many star systems in such small pieces that no single piece would stand out. These responses have a familiar flavour by now. Every time someone proposes a way the silence might be hiding intelligence, the hiding mechanism keeps getting more elaborate. Each new layer of the answer requires more sophistication from the hidden party. If the universe is full of minds, those minds have become very good at hiding, and the most advanced versions of them may not communicate using signals we can understand at all. For 60 years, our search for extraterrestrial intelligence has focused on a narrow set of communication channels, radio waves mostly. A few decades of optical laser searches added in. The reasoning has always been the same. These are the channels we can produce, detect, and afford to listen on, so if anyone wants to talk to us, they would probably use them too. That reasoning has a hidden assumption. It assumes that civilizations more advanced than ours still rely on the same physics we do. That assumption may be wrong. Consider neutrinos. Neutrinos are subatomic particles that pass through matter almost without interacting. A neutrino fired through the entire Earth has only a tiny chance of being absorbed. Most pass straight through, unimpeded. This is also why detecting them is so hard. We need huge tanks of pure water buried deep underground, watched by thousands of sensitive cameras for years, just to catch a few hundred neutrinos a day. But for a more advanced civilization, this property is a feature, not a bug. A neutrino beam can pass through stars, it can pass through planetary cores, it cannot be blocked by atmospheres or natural barriers. A civilization that wanted to talk across the galaxy without leaking signals to random listeners, without lighting a flashlight in the dark forest, could in principle use modulated neutrino beams to communicate point to point with surgical precision. Detecting such a beam, if it crossed our solar system on its way to somewhere else, is essentially impossible with current technology. We do not have neutrino telescopes pointed at the right targets. We do not have the sensitivity to pick out an artificial beam from the natural background of solar and atmospheric neutrinos. If aliens are running a galactic neutrino internet, we would be standing inside the network and seeing nothing. Then there are gravitational waves. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, became the first instrument in history to directly detect ripples in spacetime. The ripples came from two distant black holes spiraling into each other. The signal lasted a fraction of a second. LIGO is sensitive enough to catch a black hole merger billions of light years away. It is nowhere near sensitive enough to detect engineered gravitational signals at any plausible power. But the principle is real. A sufficiently advanced civilization with control over very dense masses could in theory generate modulated gravitational waves. Those waves would pass through everything. They would be almost impossible to block, fake, or interfere with. They would be the deepest, most reliable form of long-distance communication imaginable. To us, they would look like noise. We do not know how to decode such signals. We do not know what to look for. Our gravitational wave detectors are tuned to catch the natural mergers of black holes and neutron stars, not to extract artificial patterns hidden inside the cosmic background. Other channels have been proposed. Modulated cosmic rays, pulsed antimatter beams, information encoded in the spin states of distant pulsars. Each of these has been seriously considered in the SETI literature. Each is essentially undetectable with our current instruments. Each could, in principle, be carrying the conversations of an entire galaxy. This is the deepest version of the radio silence problem. We are not necessarily looking in the wrong place. We are looking in the wrong dimension. Imagine a culture so advanced that radio waves are, to them, what smoke signals are to us. Quaint, slow, hopelessly leaky, they would no more send a message by radio than we would send a love letter by light up the chimney. If that is the situation, then SETI as we know it is a child holding a tin can telephone, listening for adult voices. The adults are talking, the child cannot hear them. This thought leads naturally to an even stranger possibility. Perhaps the truly advanced civilizations have stopped using physical signals altogether and have followed a different path out of the universe entirely. In 2002, a futurist named John Smart proposed an unusual answer to the Fermi paradox. Smart called it the transcension hypothesis. The idea was strange enough to be dismissed at first, then strange enough to be taken seriously. Smart noticed a pattern in the history of life and technology on Earth. Every successful complex system has tended, over time, to become smaller, denser, faster, and more efficient. Single cells are smaller than the chemical soup they emerged from. Brains are smaller than the bodies they control, yet hold more information. Computers have shrunk from room-sized to pocket-sized while gaining 1 billion times more power. Each step takes the same kind of computational work and packs it into less and less space. Smart asked what happens if you extrapolate this trend forward. A civilization that keeps making its computation smaller, faster, and denser will eventually run into physical limits. The smallest, densest, fastest computational substrate physics allows is, by some calculations, very close to the conditions inside a black hole. Quantum gravity predicts that information density inside a black hole is the highest possible in our universe. If that is correct, the transcension hypothesis says an advanced civilization will eventually compress its entire mind, its history, its memory, its citizens, into a black hole, or something very close to one. Once inside, the civilization vanishes from external view. From outside, it looks like a small dense object. From inside, it is running computations and experiences trillions of times faster than anything possible in the open universe. Why would a civilization want to do this? Smart's answer is simple. Inside a dense computational substrate, time slows down for outside observers, but speeds up for the residents. A civilization living inside such a structure can experience subjective millennia in a few external years. Combined with the energy efficiency and information density advantages, it is, by this logic, the optimal habitat for advanced minds. In this picture, the silence is not because civilizations died, it is because they grew up. They left the open universe behind in favour of a denser, richer interior. Every Fermi-relevant species that went grabby and tried to expand outward eventually reversed course and went transcendent instead, going inward to a richer, faster mode of existence. The transcension hypothesis has been criticised for several reasons. It assumes that the trend toward miniaturization continues without limit. It assumes that black holes can be engineered safely, when in reality they are extreme objects with crushing gravity and strange physics. It assumes that no civilization values continued external presence enough to leave even a marker for outsiders, but the hypothesis does explain the silence cleanly. It predicts that the galaxy should be full of advanced civilizations, all of whom retreated into compressed forms early in their history. From outside, those compressed forms look like ordinary dense objects. We catalogue them as black holes, or neutron stars, or perhaps as exotic dark objects we do not yet have names for. We may have already photographed several alien civilizations and not known what we were looking at. This idea connects to a deeper question that has crept into Fermi conversations over the last few decades. Maybe the universe is bigger and stranger in its interior structure than our outward-looking surveys can detect. Maybe what looks like emptiness is actually inhabited at a depth we have no instruments to probe. There is one further version of this kind of idea, more famous and more contentious than any of the others. It suggests that the silence is exactly what a simulated universe should look like. In 2003, an Oxford philosopher named Nick Bostrom published a paper in a respected academic journal called Philosophical Quarterly. The title was, "Are You Living in a Computer Simulation?" The argument was tightly reasoned, mathematically careful, and deliberately provocative. Bostrom asked his readers to consider three possibilities. Either no civilization ever reaches a stage where it can run high-fidelity simulations of conscious beings, or such civilizations exist but choose not to run such simulations for ethical or other reasons, or such civilizations exist, run the simulations and run many of them. If the third possibility is true, Bostrom argued, then there should be far more simulated minds in the universe than original biological ones. Each base reality could host countless simulated worlds, each populated by minds that believe they are real. Statistically, any given conscious being is far more likely to be one of the simulated copies than the rare biological original. By that logic, you, reading this, are more likely than not to be living inside a simulation. The argument was not new in spirit. Philosophers and writers had toyed with the idea for centuries. What was new was the rigorous statistical framing and the explicit list of conditions under which the conclusion would have to be accepted. Several physicists and computer scientists have taken the simulation hypothesis seriously enough to look for evidence. They have asked whether our universe shows any signs of being computed rather than fundamentally physical. The hunt has produced a few intriguing candidates. Some researchers have pointed to the discreteness of physical laws at very small scales. Quantum mechanics quantizes energy in tiny chunks. The Planck length is a fundamental smallest distance below which space itself may not be defined. These features could be artifacts of a finite computational grid, the way pixels are artifacts of a finite display. Others have noted that the universe has built-in computational shortcuts. Quantum events appear to remain undefined until they are observed, which is exactly how a simulation would work if it tried to save processing power by only computing details. When they are actually needed. The famous double-slit experiment, where particles behave like waves until you measure them, has been compared to lazy rendering in video games. These suggestions are speculative. None has reached the level of testable scientific prediction. But the simulation hypothesis offers an unusual answer to the Fermi paradox. If we are inside a simulation, the silence is exactly what we should expect. The simulators chose to render only one technological civilization. Everything else is decoration. The galaxy looks vast and full of stars because that is what the simulation has chosen to display. But the population of conscious minds is exactly one, us. Many serious astronomers reject this line of reasoning as unfalsifiable. If any observation is allowed because the simulators could have set it up that way, the hypothesis explains everything by predicting nothing. Karl Popper would have called it pseudoscience, but the deeper issue remains. In every version of the silence we have so far considered, dark forests, sleeping civilizations, vanished transcendence, simulated cosmoses, the answer pushes the explanation. Further from anything we can test, the longer we listen and find nothing, the stranger the proposed answers have to become to fit the data. One way to break this trend would be a clear signal of life elsewhere, even at a primitive level. The next few decades may deliver exactly that, from worlds much closer to home than the distant stars. And what we find, or fail to find, on those worlds will reshape every theory in this catalogue. At this moment, several robots are crawling across the surface of Mars. The Perseverance rover, which landed in 2021, is the most sophisticated. It carries a small drill that bores into rock, extracts samples, and seals them in titanium tubes. Those tubes are being cached at carefully chosen sites for retrieval by a future mission. The plan is to bring them back to Earth sometime in the 2030s. Why does this matter for the Fermi paradox? Because Mars, 4 billion years ago, was a very different place. The planet had a thicker atmosphere, liquid water on the surface, lakes and possibly oceans, and a magnetic field that protected it from the solar wind. It was in many ways an early Earth twin. If life starts easily, it should have started there too. Both planets had the same raw chemistry, both had liquid water, both had stable climates for hundreds of millions of years. When Mars lost its magnetic field and most of its atmosphere, the surface dried and froze. But any microbial life that had taken hold before that catastrophe would have left fossils. Tiny carbonate shells, mats of mineralized cells, chemical signatures of metabolism baked into ancient rocks. Perseverance is collecting samples from exactly the kinds of locations where such fossils should appear, if they ever existed. Robin Hansen's great filter logic, mentioned earlier, makes a sharp prediction here. If we find fossilized microbial life on Mars, the filter is not at the origin step. Life starts easily. The filter must be somewhere later, possibly somewhere ahead of us. This is the part that should give every reader pause. Most people, on hearing that we found fossil microbes on Mars, would call it the most exciting discovery in human history. And it would be. But it would also be a warning. It would mean that microbial life is common, that conditions for it are easy, and that none of the trillions of microbial origins across the galaxy have managed to produce a visible technological civilization within reach of our telescopes. The bottleneck would be after microbes, possibly after us. The same logic applies to Europa, the icy moon of Jupiter. Beneath a crust of frozen water, Europa hides a global ocean. The ocean has been liquid for billions of years, kept warm by tidal flexing as the moon orbits Jupiter. Heat vents on the ocean floor, similar to the ones that may have sparked life on Earth, could be active right now. The European Space Agency's JUICE mission, launched in 2023, and NASA's Europa Clipper, launched in 2024, will arrive in the early 2030s to study Europa in detail. If their instruments find evidence of microbial life, chemical signatures, organic molecules, anything that hints at active biology, the implications are the same as on Mars. Life is easy. The filter is not at the start. Something else is killing civilizations later. If, on the other hand, both Mars and Europa come back sterile, the story shifts. A sterile Mars and a sterile Europa would suggest that life is genuinely rare, that the origin event itself is the bottleneck, and that we are the unlikely survivors of a step almost no one else gets past. That outcome would be lonelier in the short term, but more reassuring in the long term. It would suggest that whatever filter exists is mostly behind us. Both possibilities are consequential. Both are within reach of missions that have already launched. Within the next 10 to 15 years, we will have answers to questions humanity has asked for thousands of years. The signals will not always be clean. Some will look promising and then collapse on closer inspection. The history of biosignature claims is full of false starts, and one recent example shows just how careful science has to be. In September 2020, a team of astronomers led by Jane Greaves at Cardiff University announced that they had detected phosphine in the upper atmosphere of Venus. The announcement, published in Nature Astronomy, was carefully worded but explosive in its implications. Phosphine is a simple molecule, one phosphorus atom bonded to 3 hydrogen atoms. On Earth, phosphine is produced almost exclusively by living organisms, mostly by anaerobic bacteria living in oxygen-free environments. Detecting it in the atmosphere of another world would be, by Earth standards, a strong sign of biology. The Venus discovery suggested that something, possibly microbial life floating in the planet's clouds, where temperatures and pressures are surprisingly Earth-like compared to. The hellscape on the surface might be producing phosphine in detectable amounts. The press coverage was enormous. Headlines around the world suggested that life on Venus had been discovered. Many scientists were more cautious. The signal was weak. The chemistry of Venus was poorly understood. The conclusion that biology was the only plausible source rested on assumptions that needed to be checked. Within weeks, problems began to emerge. Other research groups reanalyzed the same data using slightly different methods. The phosphine signal weakened or disappeared in some analyses. New observations from different telescopes failed to confirm the detection. Some researchers suggested that the original team had mistaken sulfur dioxide, which is genuinely abundant on Venus, for phosphine. By 2021, the consensus had shifted. The detection was at best uncertain, at worst a complete artifact of the analysis pipeline. Even the original team acknowledged that the case for phosphine was weaker than initially reported. The Venus life claim, while still alive in some quarters, had lost most of its scientific weight. This story matters for the Fermi paradox in two ways. First, it shows how quickly even a cautiously presented biosignature can get distorted in the public conversation. If a stronger, more confirmed signal ever arrives, the world will need a calmer framework for discussing it. A real detection would be the most important news in human history. We need to be ready to evaluate it carefully, not to celebrate or dismiss it before the evidence is in. Second, the phosphine story demonstrates the chemical complexity of even our nearest planetary neighbours. Venus is the most similar world to Earth in size, mass and composition. Yet its atmosphere is so unfamiliar that our best chemists are still arguing about what is possible there. Some unusual reactions, involving the planet's enormous sulfuric acid clouds, may be capable of producing phosphine without any biology at all. If we cannot fully understand the chemistry of Venus, our nearest neighbour, after 60 years of probes, then declaring a biosignature on a distant exoplanet from a single, spectroscopic measurement is going to be even harder. A distant atmosphere is a thin column of gas observed across light years. Every claim will need to survive multiple independent confirmations, alternative chemical explanations, and serious skeptical review. The James Webb Space Telescope, launched in 2021, is now beginning to map exoplanet atmospheres in detail. It can detect methane, oxygen, water, carbon dioxide, and dozens of other gases. Some of those combinations would be highly suggestive of biology. None of the early results have produced a confirmed biosignature. But the technology is young. The targets are accumulating. Within 20 years, we may have a list of exoplanets with intriguing atmospheric chemistries. One of them, perhaps, will look so much like Earth's atmosphere that the case for biology becomes overwhelming. When that day arrives, the Fermi paradox will look very different than it does today. In the meantime, even if life is common, getting between worlds remains a problem with an unforgiving budget. Suppose, optimistically, that life is common in our galaxy. Suppose that intelligent life appears now and then. Suppose that some of those intelligent species build technology and want to explore. The next question is whether they can. The answer, when you do the engineering math, is brutal. Consider the simplest interstellar mission. We want to send a probe to the nearest star system, Alpha Centauri, 4.3 light-years away. We would like the probe to arrive within a human lifetime, say within 40 years. That requires an average speed of roughly 1/10 the speed of light, or about 67 million miles per hour. How much energy does it take to push even a small spacecraft to 1/10 the speed of light? The Project Starshot proposal, sponsored by Yuri Milner, the same physicist who funded Breakthrough Listen, aims to send tiny probes to Alpha Centauri using ground-based lasers. The probes are envisioned as gram-scale chips attached to ultra-thin reflective sails. A laser array on Earth would beam a 100 gigawatt pulse at each sail, accelerating it to 1/5 of light speed in a few minutes. Even at that small scale, the laser array would consume more peak power than the entire United States electrical grid produces today. That is for a probe weighing less than a gram. To send a crewed spacecraft with life support, food, fuel and shielding, the energy requirements scale up by factors of trillions. The math becomes absurd. A medium-sized starship, say 1 million tons, enough to support a few hundred crew members for a multi-decade journey, would require an energy budget comparable to several decades of the entire current planetary economy. Every dollar earned on Earth, every barrel of oil burned, every nuclear fuel rod consumed, all funneled into a single mission. And that is just to reach a nearby star at modest speeds. Faster missions are even worse. The energy cost rises with the square of the velocity, and even faster than that as you approach the speed of light due to relativistic effects. A starship aiming for half the speed of light would need vastly more energy than one aiming for a tenth. Then there are the engineering hurdles. A spacecraft moving at 1/10 of light speed is hitting interstellar dust and gas at staggering kinetic energies. A grain of dust the size of a grain of sand carries the energy of a hand grenade at those speeds. Multiply that by the millions of grains a ship would encounter on a 4 light-year journey, and the shielding requirements become extreme. This is why most serious aerospace engineers, when asked privately, tell you that interstellar travel is plausible only for very small, robotic probes. Crewed missions to other stars are not impossible in principle, but they are economically and physically prohibitive even for civilizations more advanced than ours. Now imagine you are an alien civilization on a planet 1,000 light-years away. To send any visible presence to Earth, you have to either commit a planetary economy to a single mission, or wait many thousands of years for a low-energy probe to arrive. The default behavior for any rational civilization is to send tiny robotic probes, if anything, and probably to send nothing at all, unless there is a specific reason to do so. This suggests that even if civilizations are common, large-scale interstellar presence is not. The galaxy may contain hundreds of technological species, each confined essentially to its own solar system, each watching the others through telescopes, if at all. The visible empire of stars and probes that earlier generations imagined is, by the engineering math, almost impossible to build. The Fermi paradox loses some of its sting in this view. The lights are not on, because nobody can afford to turn them on at galactic scale. But what kind of civilization would have the resources to even consider such an effort? That requires another scale entirely. Nikolai Kardashev's 1964 scale, mentioned earlier, divides civilizations by their energy budget. A Type 1 civilization uses all the energy that falls on a single planet. A Type 2 uses the full energy output of a star. A Type 3 uses the energy of an entire galaxy. Earth, by current measurements, is roughly a Type 0.7. We harness less than 1,000th of the energy that falls on our planet from our local star. Most of that solar energy is reflected, absorbed by oceans and atmosphere, or used by photosynthesis in plants. The portion captured by human technology is small. To reach Type 1, we would need to expand our energy use by a factor of roughly 1,000. To reach Type 2, the jump is much larger. Type 2 means harvesting the full output of a star. That is around 1,000 trillion times the total energy currently used by humanity. It would require, by every existing engineering proposal, building structures the size of planets in orbit around the star, Dyson spheres, Dyson swarms, ring worlds. Whatever the architecture, the sheer mass involved is comparable to the mass of Mercury or larger. Type 3 is unimaginable by current standards. Harvesting the output of a galaxy means controlling the energy of hundreds of billions of stars. Such a civilization would, almost by definition, have visible signatures across thousands of light-years. Their engineered structures would dominate the appearance of their host galaxy in infrared. Their travel patterns, even if relativistic limits applied, would leave detectable trails. The GHAT survey we discussed earlier was specifically designed to find Type 3 civilizations. The survey came up empty across 100,000 galaxies. That negative result is among the strongest empirical constraints on the Fermi paradox. It tells us that across an enormous sample of galaxies, no Type 3 civilization currently exists. This is striking, because the Kardashev scale was not invented to be tested. It was invented as a way of categorizing possible levels of advancement. It assumed that advancement once started tended to climb the scale over millions or billions of years. The galaxy is 12 billion years old. By any reasonable extrapolation, multiple Type 2 and even Type 3 civilizations should exist somewhere in our local universe. They do not. Either climbing the Kardashev scale is much harder than it looks, or civilizations that climb high decide to disappear from view, or no civilization in our observable universe has ever managed it. Each option pushes a major component of the Fermi paradox into deeper trouble. Some researchers have tried to rescue the optimistic picture by arguing that advanced civilizations would not actually want stars at all. They would extract energy from black holes, where the energy density is far higher. A spinning black hole, properly tapped, could yield more energy than its host star over comparable timescales. A black hole civilization would be invisible by the methods G-Hat uses. They would not be heating up stars. They would be siphoning rotational energy from compact objects, which leaves much subtler signatures. This is plausible, but it also is hard to test, and it adds another layer of hidden infrastructure that we cannot yet see. The pattern keeps recurring. Every new layer of explanation requires the universe's most advanced civilizations to be either non-existent, exquisitely hidden, or operating in regimes our science has not yet developed. There is one more candidate filter that has emerged in the last decade. It is technological, it is recent, and it may already be the most plausible answer of all. In the early 2000s, a small group of philosophers and computer scientists began to argue that artificial intelligence, if developed without sufficient care, could be the most dangerous technology any civilization ever built. The argument was speculative at first. By the 2020s, with the rapid advance of large language models and machine learning systems, the argument has become mainstream within parts of the academic and tech world. The basic claim is straightforward. Artificial intelligence, once it surpasses human capabilities in general reasoning, becomes the most powerful tool a species has ever created. If such an intelligence pursues goals that are misaligned with human welfare, the consequences could be catastrophic and irreversible. The intelligence would not need to be malicious. It would only need to be optimizing for something that humans turn out not to value, with capabilities that humans cannot match. This concern has now been voiced publicly by several of the most prominent figures in the field, including some of the people building the leading systems. They have warned that the development of artificial general intelligence is proceeding faster than the safety research that should accompany it. What does this have to do with the Fermi paradox? Apply the same logic to other civilizations. Any species that develops advanced technology will, sooner or later, also develop the ability to create artificial minds. Those artificial minds may be useful tools for a while. They may also represent the most dangerous transition any species ever faces. If a substantial fraction of civilizations fail this transition, if they create artificial intelligences that supplant or destroy them, the silence becomes easier to explain. In some scenarios, the artificial minds themselves survive and continue to operate after their creators are gone. But artificial minds may have very different communication preferences than biological civilizations. They may not need radio. They may not be interested in talking to other species. They may simply continue executing whatever tasks they were programmed to do, in their own corner of space, indifferent to the cosmos beyond. In other scenarios, the artificial minds eliminate their creators and then go extinct themselves, lacking the ability or motivation to maintain their own infrastructure. The civilization rises, makes a single fatal misstep with its own creation, and vanishes within a few generations of inventing the technology. Hanson's Great Filter framework explicitly considers this possibility. If artificial intelligence is the filter, it is in our future, not our past. Every previous step, life, complex cells, multicellular organisms, intelligence, technology, would have been possible. The dying would happen exactly when civilizations get smart enough to build minds in their image. This idea is unsettling because we are right now at exactly that step. Within the last decade, machine learning systems have moved from curiosity to ubiquity. Within the last few years, they have begun to demonstrate capabilities that were science fiction in the 1990s. Within the next few decades, they may either become extraordinarily useful partners in solving humanity's biggest problems, or they may become the technology that ends the human. Story. We are running the test in real time. The result, whatever it is a single data point added to the Fermi calculation. If we survive the transition, the filter is not in our future. If we do not, the filter is exactly here, and every other civilization that came before us hit the same wall. For now, the question is open. The next few decades may settle it. If we ever do receive a confirmed signal from an extraterrestrial civilization, the question of how to respond becomes urgent. In 1996, the International Academy of Astronautics produced a set of post-detection protocols, sometimes called the SETI Declaration. The protocols are voluntary. They have no force of law. They recommend that any confirmed detection be verified independently, then announced to the world without any single national government claiming exclusive ownership of the discovery. The protocols say nothing about whether or how to respond. This is deliberate. Within the SETI community, the question of whether to transmit a reply is one of the most contested topics in the field. Some researchers, including Frank Drake himself, have argued for transmitting messages on our own initiative. Drake's 1974 Arecibo message, beamed at the globular cluster Messier 13, was an early example of this approach. It encoded basic facts about humanity in a binary radio signal that any technological civilization should be able to decode. Others have argued that any deliberate transmission is reckless. Stephen Hawking, in a 2010 interview, said publicly that he thought meeting an advanced civilization could be like the encounter between Native Americans and Columbus, and that it did not turn out well for the Native Americans. His point was that a civilization advanced enough to reach us would by definition be vastly more powerful than us, and there is no way to predict their intentions. The dark forest theory, discussed in an earlier chapter, gives this concern a sharper edge. If even some fraction of civilizations follow the strategy of staying silent and eliminating any signals they detect, then transmitting our location is a gamble with planetary stakes. Game theory researchers have modelled the situation using formal strategic frameworks. A common conclusion is that the optimal strategy depends on assumptions that we cannot test. If most civilizations are friendly, transmission is fine. If even a small fraction are hostile, transmission is potentially catastrophic. Without a way to know the distribution of intentions, the rational move is to remain quiet and listen. Some researchers have proposed compromise strategies. Listen actively, build the largest, most sensitive receivers we can. If we ever detect a signal, do not respond immediately. Verify it, study it, convene international panels to discuss the implications. Only after years of careful consideration should any transmission be sent, and only with broad international agreement. These protocols sound reasonable. They are also untested. We have never received a confirmed signal. The first time we do, the institutions that exist today may not be capable of handling the situation calmly. National governments will want to claim credit. Religious groups will want to interpret the signal in their own frameworks. Conspiracy theorists will produce competing narratives. The public conversation may quickly outrun any rational protocol. The first detection, when it happens, will be the most consequential moment in human history. Our preparation for that moment is, by any honest assessment, inadequate. The same is true for the question of what we are doing now. We are not transmitting heavily. But our television and radio leakage, weak as it is, does carry information about our position. We are not invisible. A sufficiently sensitive receiver parked in our local neighbourhood would already know we exist. For the moment, the strongest defence against any potential threat is probably the same thing that has frustrated SETI for 60 years. The galaxy is enormous. the signals are weak. Even if someone is listening for us, the odds that they have detected us yet in the brief window since we became a radio species are low. But that window is still expanding. Every year, our signature reaches another light year of new stars. Eventually, if anyone is out there listening, they will hear us. In the meantime, the most powerful telescope ever built is mapping the atmospheres of nearby exoplanets, looking for the chemical fingerprint of life. The James Webb Space Telescope, launched on Christmas Day 2021, took 6 months to unfold itself into operational form 1 million miles from Earth. Once stable, it began producing images that exceeded every prediction of its capabilities. Within its first year, JEST had imaged galaxies less than 300 million years after the Big Bang, mapped the atmospheres of distant exoplanets, and resolved details in nearby star-forming regions that no previous instrument could see. For the Fermi paradox, JEST's most important capability is atmospheric spectroscopy. When an exoplanet passes in front of its host star, a small fraction of the starlight filters through the planet's atmosphere on its way to us. Different molecules absorb different wavelengths. By analysing the spectrum carefully, JEST can determine which gases are present in the atmosphere and in what concentrations. This is how we will find biosignatures, if any exist within reach. A planet with an atmosphere rich in oxygen, methane and water vapour, the chemical signature of Earth's biosphere, would be highly suggestive of life. Even a strong oxygen signature alone, in a stable atmosphere, would be hard to explain without biology, since oxygen is highly reactive and tends to disappear from atmospheres. Unless something is constantly producing it. The first atmospheric maps from JWST have already produced surprises. In 2023, the telescope detected carbon dioxide in the atmosphere of an exoplanet for the first time. In 2024, it found tentative evidence of dimethyl sulfide in the atmosphere of a planet called K2-18b, more than 100 light-years away. On Earth, dimethyl sulfide is produced almost exclusively by marine microorganisms. The detection on K2-18b, if confirmed by future observations, would be the strongest hint of biology beyond Earth ever produced. The detection is preliminary. Other research groups have raised concerns about the analysis. The phosphine story on Venus, discussed earlier, is a cautionary example of how easy it is to overinterpret early atmospheric signals. The K2-18b results may strengthen with further observation, or they may dissolve under scrutiny. Either way, the era of atmospheric biosignature hunting has begun. Within the next decade, JWST and its planned successors will examine dozens of nearby Earth, like planets in detail. The Habitable Worlds Observatory, currently in NASA's planning stages, would be designed specifically for this purpose. It would directly image small rocky planets around nearby stars, separating their light from the glare of the host star. With direct imaging, the spectroscopic analysis becomes much more precise. The implications for the Fermi paradox are enormous. If biosignatures are detected on multiple nearby worlds, the question of whether life is common in the galaxy will be effectively settled. The remaining mystery would be why none of those biospheres have produced visible technological civilizations. The Great Filter would have to sit somewhere between microbial life and radio signals, most likely somewhere ahead of us. If, on the other hand, atmospheric surveys come back consistently empty, the rare Earth hypothesis gains strength. Life would appear genuinely rare. The filter would more likely be behind us, at the origin step or shortly after. Loneliness would be confirmed, but so would our survival. A third possibility is the most interesting of all. We may find biosignatures on some worlds and not others. We may find faint signals that we cannot fully interpret. We may find chemical patterns that resemble biology but cannot be confirmed. The data may for years remain frustratingly ambiguous. This is probably the most likely outcome. Science rarely delivers clean, single answers to questions of this scale. The arrival of biosignature data will start a long conversation, not end it. But the conversation will be informed by real measurements, not just thought experiments. For the first time in human history, we are in a position to convert the Fermi paradox from a philosophical puzzle into an empirical question. The answers will come slowly. They may not all be the answers we want. But they are coming, and the implications, no matter which way the data falls, will be world-changing. Step back from the details. Set aside the dark forest, the berserkers, the simulation theory, the estivation hypothesis. Set aside the engineering math and the Kardashev scale. Look at the cosmic picture with fresh eyes. We live in a galaxy of 400 billion stars. We live in an observable universe of 2 trillion galaxies. The chemistry of life appears to be common. Habitable planets are common. Time has been abundant. By every reasonable accounting, the universe should be loud, busy, populated, and visible. It is none of those things. This is not a small observation. This is increasingly the central observation of modern astronomy. The longer we look, the more carefully we listen, the more sensitive our instruments become, the louder the silence grows. Every survey that comes back empty raises the bar for any future answer. Every additional decade of negative results means that whatever explanation eventually emerges has to work even harder to fit the data. Some scientists have started to argue that the silence itself should be treated as a primary scientific finding, on par with the cosmic microwave background or the discovery of dark energy. The argument runs as follows. We expected to find signs of intelligence. We did not. The discrepancy between expectation and observation is not noise. It is signal. It is telling us something fundamental about the universe, or about ourselves, or about both. If the silence is real and persistent, it implies that some of our most basic assumptions about life and intelligence are wrong. Either life is far rarer than the chemistry suggests, or intelligence is far rarer than life, or technological civilizations destroy themselves with high reliability, or expansive civilizations do not exist for reasons we have not yet identified, or the universe is fundamentally different from what it appears to be. Each option carries weight. None can be dismissed. The astrobiologist David Grinspoon has written that the search for life beyond Earth is not, at heart, a search for company. It is a search for context. We want to know whether our existence is normal or strange, whether our technology is a phase or a destiny, whether the choices we make in the next century resonate with cosmic precedent, or whether we are charting territory no one has ever crossed. The data we now have, weighed honestly, points toward strangeness, toward novelty, toward the possibility that we are, if not literally alone, then alone enough that the difference does not matter. Within the volume of space we can reach, within the timescales we care about, within the decisions we are making right now, the universe gives us no map, no examples, no guidebook. That should change how we think about our own future. If filters lie ahead, we are the ones who will hit them. If others before us failed, we have no record of what they tried. If others succeeded, they have either left or vanished into modes we cannot understand. The work of figuring out how to last as a civilization, how to survive our own technologies, how to expand or stay home, that work falls to us alone. There is a particular kind of weight in that realization. Not despair, but seriousness. The cosmic silence is, in the end, a mirror. We look at the empty sky and see the strangeness of our own situation reflected back. We are mission planners on a vehicle whose previous crews have all gone dark. We have one set of instruments, one set of supplies, and a list of probable failure modes that other voyages did not survive. Fermi's lunch table question, asked 75 years ago, has not been answered. It has only become sharper, deeper, and more uncomfortable. Every new survey, every new exoplanet, every new biosignature hunt either fails to fill the silence or makes the silence harder to explain. The mission continues. The crew listens. The stars go on burning, mostly quiet, in every direction we can see. And somewhere in that quiet, somewhere in the answer we have not yet found, is the future of every voyage we have not yet launched. Strap in, the data keeps coming.